Hello everyone, I'm Sourav Sinha and I'll be presenting our paper Physical Layer Attacks Against Pulse with Modulation-Controlled Actuators. In this paper, we develop IEMI-based false actuation injection attacks for PWM-controlled actuators such as servo and DC motor. The attack takes place at point 1 in the figure and is done by either blocking or altering the actuation data encoded in the PWM signals. Now, there are FAI attack waveforms for servo motor reported in the literature, but they are limited in terms of attack distance and rotation direction. These approach also assume that the attacker is synchronized to the victim PWM signal. In our work, we overcome these limitations. Our attacks work at larger distance, can rotate the servo in any direction, and don't need to be synchronized to the victim PWM. Also, compared to the IEMI-based sensor attacks, i.e. the attacks at point 2, the FAI attacks are more effective as they cannot be easily mitigated by using, for example, robust state estimators. However, these attacks require higher induced voltages that are comparable to the amplitude of the victim PWM. The PWM is a widely used actuation signal to transmit actuation data. It is a rectangular waveform with period PWM of 20 milliseconds, and the duration T high varies between 1 and 2 milliseconds and carries the actuation information. For a servo, for example, T high of 1 millisecond would mean rotation to one extreme, 1.5 would mean neutral, and then 2 millisecond would mean rotation to the other extreme. Similarly, for a DC motor, 1 millisecond is 0 RPM and 2 milliseconds is maximum RPM. An actuator computes the T high by computing the duration between the rising and the falling edges of the PWM. The goal of the attacker is to launch low power FAI attacks to block or take control of the PWM based actuators through electromagnetic coupling. To do so, the attacker must prevent the transmission of T high or modify T high. The victims are cyber physical systems with PWM actuators. It is assumed that the attacker has the dimension information of the victim circuitry, for example, the PWM cable lengths. And the attacker can either design or acquire resonant loop antennas, power amplifiers, and RF components. The major challenge for the attacker is to induce high voltages at different distances for successful attacks. The two most successful attack waveform that are reported are the block and full control waveform. A block waveform is a continuous wave signal at certain frequency that prevents the detection of the rising and the falling edges of the original PWM, thereby blocking the control of the actuators. The full control waveform consists of frequent sinusoid pulses with smaller period. These pulses mask the original PWM signal. These signals are basically high duty cycle signals, and the duty cycle is increased by decreasing the period from 20 millisecond to 2.1 millisecond. And the attacker controls the actuator by changing T rotate between 1 and 2 milliseconds. The attacker utilizes electromagnetic coupling to induce more voltage in the near field region of the antenna. The coupling ratio is calculated experimentally, and it is observed that there is a weak coupling because K is much less than 1. Now, that's why we utilize magnetic resonant coupling to transfer power, because they are efficient. They are an efficient way of transferring power wirelessly, even in weakly coupled scenarios. In this, the optimum condition is that the attack waveform frequency should be equal to the resonant frequency of the antenna, and that should be equal to the victim resonant frequency. Now, to detect the victim resonant frequency, the attacker can use either an analytical or an experimental approach. The analytical approach gives a good estimation of the resonant frequency with limited information. It is the only thing that information that is required is the length of the PWM cable. Now, the calculated analytical frequencies are 70 Hz and 175 Hz for the aileron and flap cable. The We also compute the resonant frequency experimentally, where a transmission measurement is conducted with a excitation and measurement toroid, and the resonance frequency is detected when there is a maximum transmission, and which occurs at 61 megahertz for aileron and 152 megahertz for flap. We then demonstrate the attack in an indoor environment on the ailerons of an unmanned aerial system. The attacker system consists of a waveform generator, a 20-watt RF amplifier, a zero phase shift line, and 10 are resonating at attack frequency of 61 megahertz. The aileron rotation is measured using a quadrature encoder. Block attack is carried out at a distance of 50 centimeter. The blue curve shows the commanded rotation angle that is commanded by the victim's controller, and since the actuator is under block attack, the actuator does not respond and stays at its initial position of 0 degree, as shown by the red line. The full control attack is demonstrated at a distance of 25 centimeter. In this case, the commanded aileron angle shown by the blue line is 0. The attacker changes the T-rotate at every 3 seconds to control the aileron, and the actuator is shown to respond to these commands by rotating in the desired direction by the desired amount. Now, we also study how the attack power varies with the distance. The indoor demonstration with 20-watt amplifier show that the maximum attack distance is 50 centimeter for block and 25 centimeter for full control. To study the variation, we simulate the field distribution of two ZSPL antennas. One is 35 cross 35 that is used in the indoor attack, and other is a larger one, 70 cross 70. From the figure, we see that the block attack require less power than full control attack, and as the attack increases, the power required increases. So if we increase the block distance from 50 centimeter to 2 meters, the power required is 532 watt with a larger antenna and 1.38 kilowatt with a smaller antenna. And also for full control, if we increase it from 25 centimeter to 1 meter, the power required are 611 watt and 3.3 kilowatt respectively. We also do wired attacks on DC motors, the rotational speed of which is controlled by the PWM signal. We test multiple electronic speed controllers, ESCs, with a DC motor, and then the power required at a given frequency varies with the ESC. Now, the block attack stops the operation of the motor for all ESC models. And unfortunately, the full control attack shows the same behavior as the block attack. That is, instead of controlling the speed, it stops the motor. Now, as seen in the figure, even after the attack stops at t equal to 20, the DC motor does not retain its RPM, and that is because the motor goes into the disarmed state after being left idle for 10 seconds. Finally, we demonstrate the block and full controller attacks on ailerons of UAS during flight. The ailerons affect the rolling motion of the UAS about the x-axis. We fly the UAS in stabilized mode, where the ground controller sends, or the human pilot sends, the roll set points and picks or computes the desired rotation angle and sends it to the aileron. The attacker system is mounted on top of the UAS and consists of optical transmitter and receiver, a 20-watt RF module, an a 20-watt RF amplifier, RF module, LiPo battery, and the antenna. The victim controller is programmed to initiate the attacks, and the attack signals are sent as optical signals so that they are not affected by the EMI. The RF switch modulates the attack waveform, which is then fed to the RF amplifier with an output of 20 watt. And finally, the attack waveforms are radiated by the antenna. Now, to robustly measure the rotation angle of the aileron, we use a quadrature encoder. with the isolated circuitry so that they're not affected by the EMI. Now, in the block attack demonstration, before the attack starts, the pilot sends continuously varying roll set points, and the victim controller computes the aileron angle, and the aileron is shown to rotate by those angles. But as soon as the attack starts at t equal to 0, the aileron freezes at its current position. Thus, the roll angle keeps increasing and the altitude keeps decreasing. Now, when the attack stops at around 2.2 seconds, the aircraft loses a lot of altitude and then eventually crashes. And then you can see that happening here in the video, that there is no attack, and then the pilot will send continuous roll set points and the aircraft will follow that, and then it will freeze when the attack starts and crash. Now, during the block attack demonstration, the human pilot sends 0 roll set point, and then the computed aileron is constant for that. And after that, when the attack starts at t equal to 0, the attacker sends a t rotate of -1.8 meter per second, which rotates the aileron in the negative direction, making the aircraft roll. And after the attack stops, the aileron rolls by around 180 degrees, but the victim controller successfully regains the control and then holds it back again. And then you can see in the video here that there is no attack. The attack starts rolling the aircraft, the attack stops, and the victim controller regains the control of the aircraft. So to conclude, we have shown that IEMI is a significant threat for PWM-based actuation control, and study of countermeasures are needed. Thank you.